Oh, hello. Today we're learning properties of definite integrals. So our goals are to develop algebraic properties of definite integrals so that we can manipulate them and to compare integrals by comparing their component functions. Here's our motivation. Suppose the velocity of an object is given by v of t equals t squared plus t plus 1 for t between 0 and 3. What was the object's displacement? Okay, so if you remember your motivation last time, we should know to find the displacement, we need to integrate the rate of change of position. So we need to integrate the velocity to find the displacement. Um, Only problem is how do we do that? So we know if we look at the graph, it should be that area in between our velocity function, the parabola, and the t-axis. But we never learned any formula for the area under a parabola in school, right? So far we don't know exactly what that area is. You could approximate it with a Riemann sum, um, but actually next time you'll learn that exact area. Today we're not going to be finding that, but we're going to be thinking about properties of integrals and how to compare them and that sort of thing. So um, this is where I have to say we kind of lied to you in the last video because we defined the definite integral as the signed area in between the curve and the x-axis. Um, that's how you should think about it, but it's not the actual definition. So we're not going to be working with the actual definition, but what it really is a limit of Riemann sums where the number of rectangles goes to infinity. Okay, so I wanted to show a quick example of taking a limit of Riemann sums, at least graphically, with this function f of x here, cubic polynomial, and our interval is -1 to 2.5. So we're approximating the integral of f of x dx over that interval. And n is the number of rectangles used. So as we know, we're getting an approximation of the signed area. And as the number of rectangles increases, that approximation gets better and better. And once we get, say, to 100, it's very, very close. Not exact, but it's very close to the real value. So by the way, I just Googled Desmos Riemann sum and found a demo like this where you can input whatever function you want and see what it's going to look like. You can also change the number of rectangles, the interval, and all that. Um, D here, this is the width of the rectangles. And this is the actual signed area, 12.632. This is the left-hand sum, what that works out to, 12.55 something. Right-hand sum, 12.72, and the midpoint sum, 12.632. So these are all close, right? But the midpoint sum matches this to 3 decimal places. So that's pretty good. Um, so the fact that uh, this is a limit is going to help us to deduce properties of it. Also, the point is that how we define signed area is by the value of this limit when it exists. So that's analogous to when we define derivatives, that was also a limit. And then once we had the derivative defined as a limit, we were able to define the slope of the tangent line as the value of that limit whenever it exists. So it's the same sort of thing. And let me go back to the iPad. Okay, and so when this limit exists, you say that the function is integrable, and we're not going to worry too much about that because there's a theorem that says as long as f of x is continuous over the closed interval a, b, the integral will exist. So continuous functions are always integrable. And that is very, very useful because we know how to check if a function is continuous. Okay, so you'll learn how to do this displacement example next time. But for now, it's still helpful to know that these gadgets, these definite integrals are actually limits, because that means the limit laws are going to give us a bunch of nice properties. So for example, the sum law applied to an integral of the sum of two functions just automatically tells us that the integral of f plus g is equal to the integral of f plus the integral of g. Okay, so here's going to be a whole bunch of properties that come from the limit laws, because integrals are really limits. So if we have two functions that are continuous over the closed interval, a, b, and whatever intervals are involved, we have the sum rule we just said, the difference rule, very similar, and the constant multiple rule. So this is a constant times a function. We can pull the constant out. Okay, great. So here's one that's a little bit maybe less intuitive. So far every integral we've said, we put the smaller number on the bottom and the larger number on the top. If you switch the order there, it switches the sign of the answer. So normally you put the smaller number first and the larger number second, and that orients the interval from the smaller number to the larger number. That's sort of the standard way of doing it. And when we do it that way, area above the x-axis counts as positive, area below counts as negative. If you switch the order and integrate from 17 to 2, you've now reversed the orientation, and that reverses the sign of the area. So now area below the axis counts as positive and area above counts as negative. So in the end, it just changes your total answer by a minus sign, but it's an important thing to remember that this property exists. You might say, why do we bother with this? Well, there's a good reason. It's because we want this next property to always hold for any possible choices of these numbers A, B, and C that are showing up. So when A is smaller than C is smaller than B, this looks extremely reasonable. It says if you integrate from A until B, that's this entire area. That should be the same as integrating from A to C, integrating from C to B. So you get like A and B, and then just add them up, right? So yeah, I'll let you work this out yourself if you want, but if you take the integral from A to A and choose B to be any other real number, we know the, well, I'll justify this in the next, you don't know it yet, but you're about to know it, that integral from A to A is always 0. And so that would mean these two have to be negatives of each other. So anyway, that's a justification for why we need this property if we want this one. And we do want this one. So this is called additivity of integrals. Next, integral over a point. This is what I just mentioned. Integrating from A to A is always 0. And the idea there is that this line segment has no area, right? reasonable enough. Okay, so here's an example. We're given two integrals from -2 to 4 and from 7 to 4, and it says evaluate the integral from -2 to 7. So this is an example where I'm going to need to use this additivity property because I'm splitting up the integral from -2 to 7 at the point 4, right? So the integral or the additivity property tells me that this integral is the same as first going from -2 to 4, followed by then going from 4 to 7. And that's a useful thing to do because I know from -2 to 4 is 8. And I know from 7 to 4 is 5. So that means if we switch it and go from 4 to 7, by that order of integration, switching the order makes it negative, or the negative of what it was before. So this is 8 plus -5. So the answer is 3. All right. And now just two more ideas for today. So this is where we're comparing our functions and using that to compare the integrals that we get. So if one function is consistently greater than the other function over an interval, then its integral will be greater than the other integral, because this is a strictly larger area. So that's just a simple shaded region sort of idea. And using that, we can get something that just is a little more like useful. So this is called the max-min inequality. It's the same idea as before, where we're comparing f, our interesting curvy function, to constant functions. So here, little m is the min of f over the whole interval, or just some number smaller than any possible value of f. And you can think of capital M as the max. So on the picture here, f of x is always greater than this value here. So I could choose that as m. And this is my capital M. And I guess in this picture, we can actually count that that's 5. And this is 12. And in black there is, or in blue there is my f of x. So the integral of f of x is in between this smaller rectangle and this larger rectangle, right? So the area of the smaller rectangle is 5 times the length of the interval. So in this case, that's 5 times 10 is less than or equal to the integral of f from 5 to 15. And then that's less than or equal to the integral of just the constant function. So the area of the big green rectangle there, which is 12 times the length of the interval. So 12 times 10. So that gives you some approximation. It says it's in between these two numbers. So here's an example using the max-min inequality. Show that the integral from 0 to 5 of square root x plus 4 dx is in between 10 and 15. All right, so that means I should try to figure out what's the min value and what's the max value of this function over this interval. Oh, that sounds like something you learned how to do. So I won't go through like using the derivative test or anything like that, but you probably remember square root functions are increasing. right? So the min is going to be the value at the left endpoint, and the max is going to be the value at the right endpoint. You could also deduce that it's increasing by taking its derivative and noting that this is always positive. So anyway, our min, our little m, is going to be square root of 0 plus 4. So our interval is 0, 5. Square root of 0 plus 4, which is 2. And our max, big M, is going to be the value at the right endpoint, square root of 5 plus 4, which is 3. Now, the length of our interval, b minus a, right, is just 5 in this case. So that tells us that 2 times 5 is less than or equal to the integral is less than or equal to 3 times 5, right? And obviously, these are the numbers we were supposed to get. So that's all we have to do. If you want an explanation, you can say by the max min inequality. Okay, so here's the try yourself problem. Find the values of a and b that maximize this integral, assuming a is less than b. So for this, I suggest thinking about the graph, sketching the graph of that parabola. You may have to factor it to find the zeros, use sort of your pre-calc knowledge of what parabolas look like, and your knowledge about signed area to think like, by changing where A and B are, what's the largest possible area I can get? So give that a try. The answer is 2 and 5. All right.